Now that we talked about areas and curves, the next natural step is to talk about volume. And there's a couple of approaches that we'll take to volume here. And in this first part, we're going to consider talking about volumes of solids by slicing them in certain ways. We'll talk about cross-sectional areas. We'll talk about using the disks and washer method. And then in the next video, we'll talk about the method of cylindrical shells. And so for now, let's go ahead and talk about how we can find volumes of objects by slicing them in certain ways. So we're going to start here with this question here. We have a solid S built up of an ellipse in the base, as we see here, red. Okay, and this ellipse has this equation for its boundary, 9x squared plus 4y squared equals 36. That's the equation of an ellipse. And we want to consider cross sections of this shape where we cut isosceles right triangles and the hypotenuse is in the base. So let's kind of draw a picture of what we're looking at here. So let's say that I slice this way here, and this black line is the hypotenuse of my right triangle. So if I look at it from the side, which I'll try to draw here, if I look at it from the side, I'm going to have a shape that looks something like this. We have a right angle there at the peak, and these two lengths are the same. Now, how can we figure out the hypotenuse of this triangle? Well, the hypotenuse of this triangle, okay, if we think back to what the mantra was for area between curves, top minus bottom, distance across here is just distance from here at the top to the one at the bottom, top minus bottom. But now that we have something that looks like a level curve, a function of two variables, we need to figure out how to get that as a function of x. And we can easily do that just by solving for y. So let's do that off to the side here. We have 9x squared plus 4y squared equals 36. That's the equation of an ellipse. And we'll go ahead and subtract 9x squared from both sides. We have 4y squared equals 36 minus 9x squared. Now I'll divide both sides by 4. So y squared is equal to 36 divided by 4. That is 9. And 9 over 4 is just 4. And now I'm going to go ahead and take square roots. And just for the, actually, let's go ahead and write out both square roots here. We'll have plus minus here in the square root. 9 minus 9 over 4, x squared in the square. Now, take note here that the square root there, okay, we can't separate square roots by addition and subtraction. We can only separate by multiplication and division. So that thing that we have up there right above me, that has to stay alone. So now let's go ahead and label the two branches here. The top branch is the plus branch, so that's 9, square root of 9 minus 9 over 4x squared. And then the bottom branch is negative 9 over minus 9 over 4x squared. So if we think about top minus bottom here, that gives us the length across, which will tell us the hypotenuse of our right triangle. Well, we subtract here, this top thing minus this top thing here, well, the minus turns into a plus there, so I have two copies. So this hypotenuse here, okay, will be 2 times the square root of 9 minus 9 over 4 x squared. That's the hypotenuse. Now, we have the hypotenuse, but I really need the side length of this triangle because that helps me figure out the area of the triangle. Well, this is an isosceles right triangle. Let's go ahead and make a note of that there. An isosceles right triangle. We can remember one of two things here. We know that the right triangle here has both of its legs here equal to the same length s. And so we can use the Pythagorean theorem to figure out what s needs to be. Okay, s squared plus s squared equals this hypotenuse squared. Or you can remember the basic rule from geometry. Just to drive the point home a little, let's go ahead and derive this using the Pythagorean theorem. So our unknown side length is s. So we'll have s squared plus s squared equals this thing squared So let's go ahead and write in what that should be. We'll have 9 minus 9 over 4 x squared into square roots squared. We have 2s squared equals, well, how do I square this kind of thing? Take the square of each part individually. 2 squared is 4. Squares and square roots cancel. Kind of thing right here. Now I can just divide by 2 and take square roots once again. And when we do that, we get that s is equal to square root of 2 times 9 minus 9 over 4 x squared. Okay? And we remember that the area of a triangle here, half the base times the height. So now we have the area of one of our cross sections located at some position x. Let's go ahead and put that here somewhere. The area of a cross section at position x, it'll be 1/2 times the base times the height, but the base and the height are the same, so it's 1/2 s squared here. Go ahead and write that in. 2 in the wrong place. So we have 2 times 9 minus 9 squared, all in the square root squared. And well, we can clean that up here. Get 1/2 of 2 times 9 minus 9 over 4 x squared. And while the 2's drop there, I have 9 minus 9 over 4 x squared. And so this is the area of one of our cross sections. And this helps us because to get the volume of what the solid looks like, I just now integrate across using that area function. So the total volume, right, that here is something that we need. The volume here is an integral of our area. Now, this shape has a special kind of construction that we can use to like make our work easier, which I will do in some of the following problems. But let's go ahead and write out what this should be. Okay, we can see in our picture here that the highest x value is 2 and the lowest x value is -2. You can also get that by finding the zeros, okay, of that square root function that we derived earlier. But with that done, we can now say that the volume of this thing is the integral -2 to 2 of our area function right here. Go ahead and make that emphasize there. We integrate our area function, x, and we can actually use some symmetry here because this object is symmetric about the y-axis. I can just integrate from 0 to 2 and take twice that, and I'll get my total volume. But to go ahead and demonstrate how this thing works, we'll just go ahead and work out the integral as usual. So what that means is we'll just use our power rule again, handy power rule. 9x minus 9x cubed over 4 times 3, so that's 12. Evaluated between 2. We'll go ahead and punch in what we type in our calculators. So 9 times 2 minus 9 times 2 cubed over 12. You can certainly simplify that 9 over 12 is 3 over 4. And then we'll subtract 9 times -2 minus 9 times -2 cubed over 12. Again, keeping sure that we are being careful when we do exponent stuff with negative inputs. Okay. Well, let's go ahead and see what this gives us. 9 times 2 is 18. 2 cubed is 8. 9 times 8 is 72. And 72 over 12 is 6. And it turns out we'll get the same sort of thing here. Okay, 18 minus 6 is 12, and there's 2 of them. Our volume is 24 cubic units. We're done here. And that's how we handle this basic slicing method. We're going to need this as a framework when we talk about doing discs, when we do discs and washers, because those are different, particular types of cross sections. So now let's practice with a couple of other ones where we now have a base object in the plane here. We have some other types of cross sections. In this example here, we now have a region bounded by this parabola, y equals x squared in red, y equals 4 in blue, this horizontal line. And we're going to take cross sections perpendicular to the y-axis, squares. So how do we handle that? Well, let's go ahead and draw in what a certain cross-section would. Well, in orange here, we'll go ahead and draw a slice here. This is perpendicular to the y-axis. And this is as if I'm looking at it from the top down. This is the side length of my square. Let's go ahead and make a note here. Squares. And so let's go ahead and draw a picture of what the cross-section would look like. So here's a square located, say, at some position y, okay? And we want to figure out the side length of the square because then that tells us what the area of the. Well, we need to think about, in this case, how we're slicing right minus left, okay? Well, I need these as functions of y to figure out how to get the length across. And if I solve for y, okay, in the parabola, if you solve for x, we get x equals plus minus square root y. So the left branch here is plus square root y, and the right branch here is minus. And now what's the side length? Right minus left? Well, square root of y, right up there, square root of y, minus square root of y. Well, minus minus turns into a plus. That just gives me 2 square root of y there. So the side length of my square is 2 square root y. Now the area of this square, done in a different color, the area at any position y is just 2 square root of y square, which is just 4y. And now how do we find our volume? We now integrate all the way across. Now, notice here that these cross sections are moving up and down, not left to right. And so this is an integral in y. So with that being done, the volume here, black volume, integral from 0 to 4. And why is it from 0 to 4? Because this orange strip here, at its lowest, y equals 0. At its highest, y equals 4. That's the top boundary curve of the region. And what's our area function for y? Y. And this is just, again, another power rule exercise, right? Add 1 to the exponents, we get 4y squared, and divide by the new exponent, divided by 2. Okay, 4 divided by 2 is 2, so the antiderivative is 2y squared. Evaluate on the boundary. Go ahead and write in what we would punch in. 4 squared minus 2 times squared. Well, 4 squared is 16, times 2 is 32. Of course, when we evaluate at 0, we get 0. Volume is. So once again, it's another application here of our integration, and we're connecting it with our area between curves that we learned last time, remembering top minus bottom, right minus left. Go ahead and look at another one here. We're going to find the volume of a solid whose base is this triangle region with vertices 0, 0, let's mark them in, 2, comma 0, so that's this point, and 0, comma 1, and the cross sections are perpendicular to the x-axis. They are semicircles. So now let's think about what our cross sections would look like here. So I'm going to go ahead and first fill in what this triangle look like. Try to do it in a similar looking color. Oh, so let's go ahead and make it purple. Okay, so we now have this triangle bounded in purple. And I'm going to go ahead and draw in one of the cross sections here. Let's do it in this sort of gray color. So this is a strip here that represents the diameter of a semicircle, as if I'm looking at it from the top down. And now let's look at it from the side. Let's look at the side view here. This is a semicircle. Well, I need a diameter, which is the length, okay, here, top minus bottom, but we need to figure out what that boundary curve is. And since this is a triangle, okay, one of those boundary curves is a line, so I just need the equation of the line that goes through 0, 1, and 2, comma 0. And so let's first go ahead and find the slope of that line. Okay, so we think about the slope of this line. It's a change in y over change in x. Rise over run, right? 0 minus 1 over 2 minus 0. Slope is minus 1/2. And notice that we already have the y-intercept, right? 0, 1. Y-intercept is where the line crosses the y-axis. So this line here is y equals negative 1/2 x plus 1. And so for any x, what is the length of this gray strip here? Top minus bottom again. Negative 1/2 x plus 1 minus 0. Well, it's just negative 1/2 x plus 1. So the diameter here is negative 1/2 x plus 1. But how do we find the area of a circle? Well, the area of a circle is equal to pi times the radius squared, but I have a diameter here, not a radius. And I also have half the circle. So that means the area of the semicircle is half of pi r squared. But then to get the radius, I take half the diameter. And so in this case, the radius will be half the diameter, half of minus 1/2 x plus 1, which is just minus 1/4 x plus a half. Okay. And now I have everything I need to figure out the area function. So the area of one of my cross sections here, because it's a semicircle, we're going to take half. We'll have half of pi times my radius squared. We take that thing that we did above and square it. And let's go ahead and multiply it out. So 1/2 pi, that's just pi over 2. Now when I multiply out the inside, I get 1 over 16 x squared. Okay. Now I'll need to do 2 times the first thing times the second thing. 2 times a half is 1. Times negative 1/4 is negative 1/4. We have minus 1/4 x. And then plus the second thing squared, 1 over 4. Okay, you can clean that up if you want, but for our integration, this actually works out nice. Okay, and so now where are we integrating from? Well, lowest x value is x equals 0. Highest x value is x equals 2. So our volume will be the integral from 0 to 2 of our area function. Pi over 2 times this thing here. We can discard any common factors if we want to. Okay, x. And in fact, what I will do is go ahead and I'll go ahead and throw out factor of 1 over 4, okay, from this parenthetical thing here. So let's first pull out the pi over 2 as a constant. And then I'll go ahead and pull out a common factor of 1 over 4. Okay, so we'll have 1 over 4 times 1 over 4 x squared minus x plus 1 dx, just to make our work a little bit easier. We don't have to do that. Okay. And now I can absorb the 1 over 4 into pi over 2 into a pi over 8. And now I'm going to look at the antiderivative of this parenthetical stuff here. Well, power rule once again, x cubed over 12, right? Add 1 to the exponent, divide by that new exponent, minus x squared over 2 plus x. Okay, evaluate between 0. And once again, good idea to write in what you're going to type in right before you type. 2 cubed over 12 minus 2 squared over 2 plus 2. That's kind of there. And then minus everything at 0, but of course, when we evaluate at 0, you should be able to see you get 0. Okay, now we just do some of the hard calculator work here. 2 cubed is 8. You get 8 over 12. Minus 2 squared, that's 4. Over 2 is 2. Plus 2. Okay, well, 2 minus 2 is 0. Then we have pi over 8 times 8 over 12, the eighths drop, and we just get a simple number. Pi over 12. Pi over 12. Over 12. So what's the general idea here? Find the area of one small cross section, and then we're going to integrate all across our solid, across our base, which means that we're going to add up these little tiny cross sections and glue them together to get a volume. And that's going to be the general idea moving forward here. Okay, and the next set of problems in the next part, we will go ahead and talk about how to talk about finding volumes by the method of slicing with discs and washers. Those are special types of cross sections. I'll see you in the next one.